Modern office buildings rely heavily on manual delivery systems for transporting documents, packages, supplies, and food between rooms and departments. These repetitive delivery tasks consume time, reduce efficiency, and become increasingly difficult to manage in large, high-rise environments. To address this problem, we developed PicoBot, a smart indoor delivery robot designed to automate room-to-room transportation inside office buildings. One of the primary focuses of this project was designing a robotic system architecture that balanced reliability, efficiency, and future scalability within an indoor delivery environment. At the center of PicoBot's system is the UKIT Explorer microcontroller, which functions as the main processing and control unit for the robot. The motors control the robot's movement, including forward motion, turning, and stopping during operation. For destination recognition, PicoBot uses a Raspberry Pi camera mounted on the side of its chassis. An ultrasonic sensor mounted at the front of the robot detects nearby obstacles. A Bluetooth communication chip enables wireless communication between the robot and an external computer system, supporting QR code processing and future system expansion. To navigate, the PicoBot uses a UKIT color detection sensor that scans for white tape placed along predetermined pathways. This simulates what would be installed in the real business. In this example, the robot demonstrates its capabilities along a line path that simulates its real-life operating scenario. It begins at an origin point in the space, and then follows the line path with a turn as it would navigate in a real office building. Along its path, on its sides, it encounters QR codes that for this prototype act as the destinations where the robot is directed to arrive for successful delivery. Then it activates its return route to go back to the origin and prepare for another ride. To apply the mechanisms of the robot for the product's intended use, we also prototyped the shelf space made out of cardboard for the items to be placed on. We wanted to test that the robotics mechanism was strong enough to operate with the added weight. It showed that it was capable. What makes PicoBot unique is that the prototype was designed not simply as a demonstration robot, but as a scalable foundation for a realistic smart delivery ecosystem. Rather than focusing only on movement, the project integrates environmental recognition, navigation logic, and delivery infrastructure into a single coordinated system. The QR code recognition mechanism establishes a framework for future intelligent building integration. This creates opportunities for advanced features such as RFID-based room authentication, automated access systems, and dynamic delivery routing. Additionally, the navigation logic was intentionally designed to be adaptable beyond office environments. The same architecture could potentially be expanded for applications such as hotel service robots or autonomous food delivery systems. The project emphasizes modularity and scalability, allowing future upgrades without requiring a complete redesign of the platform. During development, several core systems performed successfully, including autonomous navigation, QR code detection using pre-trained AI, ultrasonic obstacle stopping. However, some aspects were less successful, including implementing the Raspberry Pi display and using cardboard for the shelf structure, which reduced durability. Since this was our first time working extensively with the robotics hardware, becoming familiar with the components and the system integration was also time-consuming. One major challenge was developing the wireless QR code detection mechanism because it required working across multiple programming languages and systems. This was overcome through repeated testing and consultation with Ajahn Sunny. In future iterations, we aim to develop a life-size prototype with additional ultrasonic sensors around the chassis and shelf system for improved spatial awareness. Other planned improvements include a clearer signaling system, an onboard touchscreen interface, RFID or expanded AI-based destination recognition, advanced pathfinding that does not rely on floor lines, and future elevator coordination for multi-floor delivery capability.